All right, welcome. Today is January 27th, 2020. We're doing a game plan meeting right here, right after Brady's lecture on binary and decimal numbers and hexadecimal and CS24 underscore Tico. What's up, Catherine?
I'm so hungry.
Hey, you could have gone straight to lunch, but I would have been talking to myself in this thing here. Let's go ahead and open that up and let's get this bad boy going, Catherine. Can you open up that repo and we can just go through it real quick?
Okay, give me 1 sec.
All right. There's Bryant.
Hey.
What's up, man?
Hey, not much.
Catherine's about to hop back in here and we can she's gonna share the README and then we'll just go over it real quick and we'll be all good.
All right.
Oh, there's Jade too. Awesome. All right. Catherine's gonna be sharing. Let's go over this bad boy today. Catherine, I believe you're on mute.
Oh, sorry.
Okay, all right. Yeah, let's just read this and get an inventory of everything that we have and then figure out what we're gonna do.
So it's computer architecture. There's a task list to add this to the first comment of your pull request. So there's multiple days. So day 1 is get print 8.ls8 running. Inventory what is here. Implement the CPU constructor. Add RAM functions, RAM read and RAM write. Implement the core of run. Implement the HLT instruction handler. Add the LDI instruction. Add the PRN instruction.
Okay.
So, and then there's other days. Day 2 is add the ability to load files dynamically. Get molt.ls8 running. Unhard code the machine code. Implement the load function to load a .ls8 file given the file name passed in as an argument. Implement a multiply instruction, run molt8.ls8. Day 3 is stack. Implement the system stack and be able to run the stack.ls8 program. Day 4, get call.ls8 running. Implement the call and RET instructions. Implement subroutine calls and be able to run the call.ls8 program. And a stretch is to add the timer interrupt to the ls8 emulator. Add the keyboard interrupt to the ls8 emulator. Write an ls8 assembly program to draw a curved histogram on the screen.
Wow. It's a pretty crazy stretch.
Here, I can click on this. There's another README. Okay, so project the ls8 emulator, implementation of the ls8 emulator, objective to gain a deeper understanding of how a CPU functions at a low level. We're going to write an emulator for the world famous Lambda School 8 computer, otherwise known as ls8. This is an 8-bit computer with an 8-bit memory addressing, which is about as simple as it gets. An 8-bit CPU is one that only has 8 wires available for addresses, specifying where something is in memory, computations, and instructions. With 8 bits, our CPU has a total of 256 bytes of memory and can only compute values up to 255. The CPU could support 256 instructions as well, but we won't need them. For starters, we'll execute code that stores the value 8 in a register, then prints it out. So print 8.ls8 prints the number 8 on the screen. There's something with the LDI R at 0, 8. Some binary. PRN, I'm guessing, is print, R at 0. Some more binary. And then halt, I'm guessing, is stop. More binary.
Let's stop right there real quick, just so we kind of get a better idea of what's happening in that small bit of code. So that first line, what would you guess? What would you guess from the comments that it's doing?
I don't know what LDI is.
Mm-hmm. But what do you see after LDI?
Register 0.
Mm-hmm.
R0
And
would be the register 0 and something with like the number 8, which would be an input.
Right. So how many inputs would you say? So let's pretend that each one of these lines represents a function, right? This function is called LDI, then the other one's called PRN, and the other one's called halt. How many inputs does halt take?
1.
Try again.
That's halt right there.
Yeah, right here. This is halt, but how many inputs does it take?
Oh, it doesn't take inputs. It's just 1. But I thought you meant like for binary. Like
Correct.
how many?
It doesn't take any inputs. And actually another way to know is, check this out. So obviously there's nothing after halt, right? So after PRN, we have R0, which represents what?
Register 0.
Correct. Yep. So that takes in 1 argument. And
0 index.
And then LDI takes in how many arguments? 2. Right, now check this out. So if you look at the first 2 numbers of that, I guess the binary instructions, that's 0, 0, that's binary for 0, right? What's this in binary?
If it's just 0, 1,
Mm-hmm.
well, that would just be, it depends where it's at, because if that's just 1.
Exactly. So that tells you there the first 2 digits will tell you how many arguments you're supposed to have in the function. So what do you think?
The top
one
one takes 2 because the 1 is in the second place.
Exactly. Yep. So that's how you would know if you're calculating these correctly and doing these correctly. So little trick there. Okay, go ahead and continue reading on.
The binary numeric value on the left in the print 8LS8 code above is either the machine code value of the instruction, e.g. this number for LDI, also known as the opcode, or one of the opcode's argument, these numbers here and here, which are those for the value 8, also known as the operands. So opcode or operands. Mm-hmm. This code above requires the implementation of 3 instructions. LDI, load immediate, stores value in the register or set this register to this value. PRN, a pseudo instruction that prints the numeric value stored in a register. HLT, halt the CPU and exit the emulator. See the LS8 spec for more details.
We don't go into that because that is what you guys will be doing this afternoon. There's a lot of documentation, so that's what you guys are supposed to be doing. Okay. But as long as you understand the overall idea.
Okay. So the above program is already hard-coded into the source file cpu.py. To run it, you will eventually Python 3 lsapy. But you'll have to implement those 3 above instructions first. So we could put these instructions to get that to work in that file, which they gave to us. So step 0, important, inventory what is here. Make a list of files here. Write a short 3 to 10 word description of what each file does. Note what has been implemented and what hasn't. Read this whole file. Skim the spec. I don't know what that means. Okay, step 1.
Which part don't you know what it means? The skim the spec?
Skim the spec.
That's like the LS-8 spec right up top, that link that I told you not to click on, because you'll be clicking on it later, and it's just a ton of these functions basically.
So just skim it. Okay.
Yeah.
Step 1, add the constructor to cpu.py. Add list properties to the CPU class to hold 256 bytes of memory and 8 general purpose registers. Hint, you can make a list of a certain number of zeros with this syntax, which is what Brady did in class. Also, add properties for any internal registers you need, e.g. PC. Later on, you might...
What's PC again? Do you guys remember what PC
is what index of the register, or memory, what the index of the memory you should, the thing of instructions in memory you should apply.
It's like a pointer, right?
Yeah. Because memory is an array and the PC is the index of that array. Later on, you might do further initialization here, e.g. setting the initial value of a stack pointer. Let's see, step 2, add RAM functions. In CPU, add method RAM read and RAM write that access the RAM inside the CPU object. RAM read should accept the address to read and return the value stored there. Raw write, oh, is that raw write or RAM write? Is that a typo?
No. Yeah, actually, I think it is a typo.
All right, RAM write should accept a value to write and the address to write it. So inside the CPU, there are 2 internal registers used for memory operations: the memory address register and the memory data register. The memory address register contains the address that is being read or written to. The memory data register contains the data that was read or the data to write. You don't need to add the memory address register or memory data register to your CPU class, but they would make handy parameter names for RAM read and RAM write if you wanted. We'll make use of these helper functions later. Later on, you might do further initialization here, e.g. setting up the initial value of the stack pointer. Step 3, implement the core of CPU's run method. This is the
Catherine, I think we can, let's just, the rest of us just quickly skim through these last few steps, because I think you can stop at step 8 today is your goal, to try to print LS8, right? So just look through that real quick and see if there's anything in there specifically that you want to ask a question about, just so we can stay consistent with our time frame that we're shooting for. Oh, check out step 7. Look at the code snippet that they have there. It says print sys.argv. Does anybody have any questions on what sys.argv is again? Or you guys dealt with that when you first learned about Python? Any questions? Everybody understands what sys.argv is?
Yeah, this is 0, 1. Yeah.
Mm-hmm. Okay. All right, cool. Anything, Jade, Bryant, anything that you guys particularly have a question about?
I think there's just so much here that I still need to
Process
comb,
it, yeah.
process and comb through it. So I don't have any questions as of right now.
Okay. I would definitely say use that code that he dropped in the CS24 channel as kind of like a diving point, like where you can jump off of. It's gonna be very similar to that. Yeah, just use that as a jumping point. And then, like, as you go through this, if you get any questions, just, you want to loom me or DM me, do that. So I'm sure you guys are hungry, want to get some lunch. Make sure you sign up for time slots for the mock interview that I dropped in the channel there. And
for the mock interview, it's just going to be on stuff we went over today, correct? Or other stuff?
It's just going to be like a simple code challenge like we always do on Mondays.
Oh, okay. Yeah, that's right. Thanks.
Yeah. So. All right, guys. Good luck.
Thank you.
See ya.
Yeah.
Yeah.